Hello, I would like to welcome you to lecture 23 of 2FH3. We'll discuss today the magnetization of materials, classification of matter, and magnetic boundary conditions. We covered chapter 8 from the book of Sadiko, pages 350 to 362. As I mentioned in the class yesterday, actually this was on Wednesday, that electrons spin around the nucleus. And these electrons, when they spin, they effectively create a current loop. The current, of course, the equivalent current will be in the opposite direction because electrons are negative charges. But this current that's flowing in this direction, it creates a magnetic moment. We agreed that if you have a current loop, a small current loop, this small current loop will create a magnetic moment, and the magnetic moment is normal to the plane of the loop. And we got the expression of this one is equal to the current multiplied by the area of the loop multiplied by the unit normal to the loop. So now, the matter has so many of these infinitesimal or tiny loops, current loops. And when there is an external magnetic field applied, they start to align themselves. So an unmagnetized material will have moments like this one. You can see every electron is spinning in a different direction, and the magnetic moments, which is normal to the plane of these loops, will be oriented in all types of directions, and the net magnetization is zero. So the material is not magnetized. But when you apply an external magnetic field B to this matter, you will notice that the loops will start, and as we explained in the lecture, will start to experience torque, and this torque will try to rotate them to align their magnetic moments with the magnetic field. So now we know there is now an internal magnetic field strength created inside this matter from this alignment of these magnetic moments. And so the total magnetic field inside is not, as I will show you later, is not H anymore. It is H plus the magnetization vector. So now we have to understand this. This is very similar to the phenomenon of polarization that we discussed for matters in electrostatics. Polarization creates electric dipoles. Electric dipoles create their own electric field. Here, very similar, magnetization creates aligned magnetic dipoles. Each one of these loops is really a magnetic dipole, as I explained in the lectures. And these magnetic dipoles, they create their own field, their own internal field. So now we move to define the magnetization vector M, which is analogous to the polarization vector in the case of electrostatics, as the sum of all magnetic moments. If you take a certain volume, you sum all the magnetic moments in that volume, and then you divide by delta V, and you try to make delta V as small as possible. Of course, of the magnetic moments of all atoms, they are aligned in random direction. This sum will give you zero, and then there is no magnetization. But when these moments are aligned in certain direction, their magnetization will be in the same direction. Notice that as we explained in the lecture, the magnetic moments, it has units of ampere meter. And when you divide it by a volume, you divide it by meter cubed. So when you divide by the volume, actually we should correct the magnetic moment here. It is current multiplied by area in the unit normal. So it should be ampere meter squared, correct? It's current by area. This is the definition of the magnetic moment. This is what we said. The magnetic moment of a loop is equal to I multiplied by S multiplied by the unit normal to that loop. So it's really ampere meter squared. So if you come here, this is ampere meter squared, you divide by meter cubed, you get units of ampere per meter. So this will give you ampere per meter. And the ampere per meter are the units of the magnetic field strength vector H. So now we know that this magnetization is really equivalent to a magnetic field created inside. So the total magnetic field inside a matter, when the external magnetic field be applied, is really H plus M. So keep this in mind. we apply an external flux density vector B. This external flux density causes these loops to align themselves. We call them magnetic loops, or we call them magnetic dipoles. And this alignment creates a magnetization vector, which is really equivalent to an extra magnetic field. Now, for linear medium, we know that the H and M are proportional to one another, and the constant of proportionality, this one here, is called the magnetic susceptibility. We had before, we talked about the electric susceptibility. This is the equivalent one, and this is very similar to what we mentioned before. The polarization is equal to the electric susceptibility multiplied by E, and this applies only for a linear medium. So now, if you put all this together, we put a matter in a magnetic flux density vector B. It causes magnetic moments. Magnetic moments align themselves to create magnetization, and this magnetization has same units as H. So the total magnetic field strength inside the matter is H plus M, and this magnetization vector is in the same direction of H. If we put all this together, we can differentiate between two situations. If we have a non-magnetic material is like air or like vacuum. It does not get affected by the application of an external magnetic field B. In that case, there is no magnetization, and the relation between them is that B over mu naught is equal to H, or B is equal to mu naught H. Now, if we have a magnetic material means it has a non-zero magnetic susceptibility. So when you apply an external field B, then this will create some magnetization inside, and the net relationship between B, H, and M is that B over mu naught is equal to the net magnetic field strength inside, which is H plus M. And for a linear medium, so this expression here will hold for linear or non-linear medium. For non-linear medium, M is a non-linear function of H. But for a linear medium, which is the case we usually handle, M magnetization is equal to magnetic susceptibility multiplying H. So now we can multiply both sides by mu naught. And this is very similar to what we had in electrostatics. B is equal to mu naught mu R, relative permeability multiplied by H. So we define the relative permeability mu R as 1 plus the magnetic susceptibility. And here we could see that the net relationship between B and H is that B is equal to mu H. Mu is the permeability of the medium, which is equal to the permeability of free space multiplied by the relative permeability, and the relative permeability is nothing but 1 plus the magnetic susceptibility. So now we know this is very similar to what we discussed before, that D is equal to epsilon E, and the epsilon is nothing but epsilon naught epsilon R E, and the epsilon R is electric susceptibility, is the relative dielectric constant is 1 plus the electric susceptibility. This is very analogous to what we discussed earlier. Let's consider an example. We have a certain region in space where mu is equal to 4.6 mu naught. So mu R, the relative permeability, is 4.6. It's a magnetic material. Once we say that mu R is not 1, then the magnetic is called the magnetic material. B is equal to 10 e to the minus y az milliwebers per meter squared. So it is B is in the z direction. It varies with y, and its units is milliwebers per meter squared. We would like to find the magnetic susceptibility, the magnetic field strength, and the magnetization vector. This is, of course, direct application of the equations just discussed. This term here, which is relative permeability, is nothing but 1 plus the magnetic susceptibility. So this term can be calculated. H, by definition, the relation between B and H for a linear medium is given by the permeability, which is 4.6 mu naught. So if we divide B by this term, then we get H. If I know H, and for a linear medium, the magnetization is nothing but the magnetic susceptibility multiplying H. So we know what is the magnetization vector as well. So if we summarize all this, the relative permeability is given is 4.6, but this is 1 plus the magnetic susceptibility. Then magnetic susceptibility is 3.6. We know that H and B are related by the permeability, which is given. It is equal to mu naught mu r. It is equal to 4.6 multiplied by mu r, and mu r, and so this mu r, this mu naught, 4 by 10 to the minus 7. This is the expression for B given. So I divided B by mu naught, this mu naught multiplied by mu r, which is 4.6. And then when you make this division, 10 minus 7 will cancel with 10 to the minus 3 to give you 10 to the 4 in the numerator. You get 1729.94 e to the minus y az ampere per meter. As you could see, H and B are pointing in the same direction. They are pointing in the z direction. And they have the same variation as well in space. They vary as e to the minus y. The last thing is to get the magnetization. And this is a magnetic material. So its magnetic susceptibility is not 0. We already calculated that. So magnetization by definition is equal to the magnetic susceptibility multiplied by H. So the 3.6 multiplied by this number. When you calculate that, you get 6,227.8 e to the minus y az ampere per meter. So magnetization has the same units as H. It is parallel to both H and B. They are all in the z direction, and it has the same space dependence e to the minus y as H and as B. Now we move to discuss the classification of magnetic materials. We know that first, materials are magnetic or non-magnetic. Non-magnetic materials, they have always mu r equal to 1. So the non-magnetic material will have mu r equal to 1. So the magnetic susceptibility is 0. They are not affected by external magnetic fields. Now this figure here shows the classification of magnetic materials. Materials that shows response or show some change when you apply a magnetic field to them. The first, so they are either linear or non-linear. For linear materials, we have the diamagnetics. Diamagnetics means that the magnetic susceptibility is negative, and in that case, mu r will be less than 1. In most cases, magnetic susceptibility is a tiny, small, negative number, and mu r will still be close to 1. So this is called diamagnetic material. The second one is paramagnetic, when the magnetic susceptibility is greater than 0, and in that case, because mu r is 1 plus the magnetic susceptibility, so then mu r will be greater than 1. For most materials, this number will be very close to 0. It's positive, but it's very close to 0, and this one here will be very close to 1. It's greater than 1, but it's very close to 1. The nonlinear one is a little bit different, because in the nonlinear one, the magnetization is a nonlinear function of the electric field. And this class here is what's called, it's named after type of iron. It's called ferromagnetics. And for this matter, the magnetic permeability is pretty large, and mu r will be very large. And the relationship between mu r and this number here, it changes with the magnetic field. This is the tricky part. It's not a constant. It change with the magnetic field. So this is really just a classification of this matters, and these ferromagnetics are used very often in building microwave and high frequency structures. This figure here shows the what's called the hysteresis curve of ferromagnetic materials. Ferromagnetic materials are non-linear materials. The relation between H and B is not linear. And maybe the easiest way to understand that is to consider if we have a bar or some sort of a rod. Actually, it's a rod of this ferromagnetic material, and we have a number of turns of a coil, and there is some current going through this one here. So we have a battery, and we connect a current. There is a current that will go through this loop. So in the beginning, in the beginning, when the battery is not connected, we are at this point here. There is no magnetic field H and there is no B. When you start to increase the current, maybe I can adjust this circuit here by having a variable resistor somewhere here, so we can have a variable resistor. So through adjusting this variable resistor, I can increase or decrease the current. So in the beginning, you start from this point. When you increase the current, and as we have seen from Ampere's law, H inside this coil will depend on the current. So H will start to increase, and the magnetic flux going through this loop, this rod will also start to increase. So you get the magnetic flux start to appearing here, flowing through this one. And the relationship between them is not linear, so it goes along that curve. Okay. Now, if we switch if we try now to decrease the magnetic field again, until we make zero current going through these loops. So we literally open the circuit at this point. So at this point here, what's happening is that we really disconnected the battery. But you could see it did not come back to that point again. The material got magnetized, and there will be still magnetic flux density even though there is no H. There is no H because there is no current. Okay, so this is a typical, it does not go back to the origin again, it goes to this point here. So the rod now has been magnetized. It's not connected to a battery, but still it has magnetic field flux density B. What you will have to do now, if you go in this direction, this means that we really switch the polarity of this battery. So what we'll have to do, we have to come here, we have to erase this battery here, and then both switch its direction. So the battery now looks something like this. So the battery is allowing current to go in the opposite direction, and when current starts to go in the opposite direction means that H is negative. So in this part here, H is becoming negative, and B starts to decrease until, for some negative current flowing in the opposite direction, the material loses its magnetization. But we need some negative current to remove the magnetization of this rod. Now we can repeat the cycle in the opposite direction. We can start to increase the current in the negative direction. H is now decreasing and B is also decreasing, and the material now, the magnet has been reversed. The material is magnetized. There is B, but the direction of B has been reversed. So B now is negative. Now if we start to increase H again by adjusting this resistor, okay, when we increase it gradually, slowly until we make zero current going through. When we have zero current going through, you could see here the material is still magnetized. It's magnetized in the opposite direction, meaning that the flux is really pointing in this direction, not in the other direction as I show you in the beginning. But still, it's still magnetized, even though there is no current going through the loop. So at this location, there is no current because H is zero. There is no current going through the loop. And then the hysteresis loop will continue until it returns to this point. So you can see now in the beginning only it follows this path, and then once it gets magnetized, it starts to go along this one here. So you increase the current, you go this direction. You decrease the current to zero, you go to this point, the material has been magnetized. You reverse the current, you go to this point, the material has been magnetized in the opposite direction. You decrease the current to zero, the material is still magnetized, even though there is no current going through, but it's a negative magnetization, so the flux in the opposite side. You start to increase the current in the positive direction, the material loses its magnetization at this point. Now if you increase the current again, you can see that there is the H and B both increases. So this is called the hysteresis curve. And the equation governing B and H in this case is that B is equal to mu naught H plus M, but M is a nonlinear function of H, and it depends on the magnetic history. So the relationship between B and H is not linear anymore. It is nonlinear because M is a nonlinear function of H and depends on the magnetic history of the matter. The material really does remember the magnetization cycles it has been through before. The last thing I would like to mention this lecture is magnetic boundary conditions. We have discussed the electric boundary conditions. We have shown that in electric boundaries, the normal components of the vector D are continuous unless there are service charges, and the tangential component of the electric field are always continuous. Here we have something similar. These are two material. This one has mu1. This one has mu2. These are the permeabilities. So every permeability here is equal to mu r, the corresponding mu r multiplied by mu naught. Now, there is a magnetic field here at this, just inside this matter, B1. There is another magnetic field here, B2. Each one of them can be decomposed into tangential and normal components. And when I say normal, I mean normal with respect to the normal to the boundary. So this is the normal to the boundary here. The same thing we do it for B1. B1 is decomposed into B1 tangential, B1 normal. Now, we apply the basic law that we have, which is Gauss' law for magnetostatics. The integral of B dot ds over a closed surface is equal to 0, and we apply it to this cylinder. This cylinder, of course, has three surfaces: the top base, the top disk, the bottom disk, and then the side surface. If I make delta H goes to 0, the side integral will disappear, and then you have only the top surface and the bottom surface. For the top surface, you get B1 normal multiplied delta S. For the bottom surface, you get B2 normal multiplying delta S with a negative sign, because you can see B2 normal is pointing opposite to delta S. Delta S is pointing outward. So if you put all this together, you get that B1 normal delta S minus B2 normal delta S is equal to 0. Or when you move B2 normal delta S to the other side, you get this expression. So what this expression tells you, that the normal component of the magnetic flux density vector is always continuous. So the normal component B1 normal must be equal to B2 normal. When you cross, so just before the interface is equal to its value just after the interface. And of course, because B is equal to mu H, this means that the normal component of the vector H is usually not continuous. Is not continuous, discontinuous. Okay, so B is continuous, normal component of B is continuous, but normal component of H isn't, because they are related through mu, and mu r here is different from mu r here. This is very similar to the result that we got from electrostatics for the vector D, but the only difference is that here we don't have magnetic charges. So there is no magnetic charge, surface magnetic charge density that would change that. This always applies for the interface between any two types of materials. The second important boundary condition to remember is the tangential is on the tangential component of the vector H. Again, we have the same thing. We have two different types of magnetic materials, mu1 and mu2. There are two types of materials really. They can be magnetic or non-magnetic. This can be air. Air is non-magnetic material. This is a magnetic field here, H2. We decompose it into H2 tangential, H2 normal. This is the magnetic field H1. We decompose into H1 tangential, H1 normal. So now, what we can do, we can select a contour which looks something like this. It crosses the boundary, and then apply Ampere's law in the integral form. The integral of H dot dl is equal to the current enclosed. And for this one, I will assume there is a surface current flowing into the page. And this surface current, as I explained before, is in ampere per meter. So when you want to get the total current, you have to multiply by the length. You multiply by this length in the cross section. So here this K is nothing but a surface current density. Let's apply Ampere's law. This integral has four edges. 1, 2, 3, and 4. The two side integrals will cancel out if delta H goes to 0. So I don't worry about them. The top and the bottom one is what matters. This one here will be multiplied by H1 tangential. So they are shown at different points, but at this point also there is also H1 tangential. This segment here will be multiplied by H2 tangential with a negative sign because they are opposite. This is delta, this is the direction of delta L, this is the direction of H2 tangential. Now, the current enclosed by this surface is the current flowing in this width, which is nothing really but K multiplied by delta W. K multiplied by delta W. So we multiplied ampere per meter by delta W, which is in meter, you get amperes. If you put all this together, you see that H1 tangential delta W minus H2 tangential delta W is equal to K delta W, or that the tangential component of the magnetic field when you cross from one point on the just before the boundary to another point after the boundary is discontinuous. Is discontinuous by the value of the current normal to the field. This is very interesting finding. Notice what's happening. So if you have, this is H1 tangential, this is H2 tangential. These two will be different only if there is a surface current flowing normal to the actually to the H and to the normal to the plane. So the normal here to the plane is this direction. This is, I'm sorry, let's try to do that. The normal here is this one here. This is AN. So you can see the current I assumed here is normal to the tangential field and is normal to AN. And if you put it in vector equation, this is the equation that we usually use. That H1 cross a normal will give you tangential component. H2 cross a normal will give you tangential component. But notice that this normal, to be consistent, is pointing from region 1 to region 2. So it is this one here. So if you apply this law in the proper way, it should be H1 minus H2, and when you say H1 minus H2, this unit normal must be pointing from region 1 to region 2. So this will give you really, this cross product will give you a tangential component in the first region. This one will give you a tangential component in the second region, but after you rotate them to make them in the same direction as K, to allow for this scalar equation. Okay, so remember, so now we have really a right-handed system. H, the H field, the tangential H field in the boundary, the normal to the boundary, and the direction of the current constitute a right-handed coordinate system. So in general, if there is a surface current, the tangential component of the magnetic field will be non-continuous, and this surface current has to be normal to both the direction of the normal to the plane and the tangential field. Otherwise, the tangential component of the magnetic field will be continuous. So this one is very similar to what we had for electric field, with the only when we said that E tangential is equal to E1 tangential equal to E2 tangential. So this one will always hold because the integral of H dot E dot dl is always equal to 0. There is no I here. But for magnetic field there is I, and that's why you get this K here in the right hand side. Now let's consider an example. We have region 1, which is at z less than 0 is free space, while region 2, which is really z greater than 0, I have a typo here. This z greater than 0 is a magnetic material for which mu2 is equal to 20 mu naught. So here in the second material, mu r is equal to 20. We are given the magnetic field in the first region. It is magnetic field flux density. Magnetic flux density is 20 AX minus 15 AY plus 30 AZ milliwebers per meter squared. We would like to find H2. We have seen examples like this before in the case of electrostatics, and the same rules apply. We will take the normal component of B and we say it is continuous, so the normal component of B2 will be equal normal component of B1. And then we try to find the tangential component of B1, and then we say it's equal to the tangential component of H1. Actually, we say it's equal to the tangential component of H2. Notice that there is no surface current. There was no mention of surface current. Then the tangential component of the magnetic field will be continuous. If you put all this together, now this is the interface. We can always start by drawing a simple diagram. This is the interface between the two materials. This is material number 2. It has mu 20 mu naught. This material number 1 it has mu naught. This here is z equal to 0, and this is z axis. So this is B1 and this is B2. We'd like to find B2. B1 is given. We apply the boundary conditions that we have. The boundary condition is saying that B1 normal is equal to B2 normal, but the normal direction is the z component. This means that B2 normal is equal to B1 normal is equal to the same z component of B1. So it's equal to 30 AZ. So now we know that. We know that it's 30 AZ. Now we move to calculate to apply the second boundary condition, which is the tangential one. If this is B1 normal, then the x and y components of B of B1 constitute B1 tangential to this interface. So it's given by 20AX minus 15AY. If you want to get the magnetic field here in this one, what you'll have to do is have to say that the magnetic field strength is equal to B divided by mu naught. Of course, I should have here mu naught for the first medium. It's mu naught, correct? It's the relationship between them is mu naught. So this is the tangential component of B1, 20x minus 15ay. I divided by mu naught. Now, in the second medium, H2 tangential is equal also to H1 tangential. So it will also be equal to 20AX minus 15AY over mu naught. So now we know two things about the field in the second medium. We know the B2 normal and we know the H2 tangential. But we have to put them either in the form of B or the form of H. H is the one that's required. So we take this term here and then we divide it by mu in the second region, which is 20 mu naught, to get the total H field. So the total H field is equal in the second region is equal to H2 tangential plus H2 normal. We already calculated this one. H2 tangential is equal to H1 tangential is given by this one. And B2 normal, we calculated that is equal to B1 normal. So, and now we have to divide it by mu2. This is the only trick here, because in the second region, B2 and H2 are related by mu naught here. So this is H1 tangential, and this is now H1 normal. So you divide by 20 mu naught. Now you can take mu naught out. You can see that the resulting magnetic field is 20AX minus 15AY. 30 will cancel with 20. It will give you 1.5. So now the magnetic field strength really is 1.5, not as high as it used to be in the first region. And of course, the units for the magnetic field strength is ampere per meter.